Sorry about that, I lost my notes. So the well width determines the maximum rate at which you can flow the charges into the well according to this equation. So you can see the well width in this equation, which we covered a few lectures ago, is one of the important factors in the maximum current that you can have that recombines in that well. And because the narrow well width limits that current, the solution turned out to be a multiple well system. So now you could imagine having not just one well, but multiple energy wells. Of course, they're all subject to an electric field, but each well limited the spatial separation between electrons and holes, allowing for efficient radiative recombination. So we now have what's called a multiple quantum well LED. So that multiple quantum well approach actually gives rise to an improvement in the efficiency, and today the quantum efficiency of a blue emitting gallium indium nitride LED is in the 70% and higher range, which is a remarkable achievement. You can actually get 70% of the electrons and holes that you produce actually creating photons, blue photons. They are now the most efficient source of light and a very low cost source. So the LED, the blue LED, has become the dominant lighting technology. Although the red LED is still using the quaternary semiconductor system, gallium, aluminum, indium phosphide, that is only used for red LEDs. But white LEDs use this blue LED, which is based on the gallium indium nitride system. In order to create white light, the blue light is actually converted by a secondary phosphor material. And that secondary phosphor material that's the most important is YAG cerium. So once you've generated blue light, the blue light produced by the gallium indium nitride LED is emitted at a wavelength of approximately 450 nanometers, and then it excites YAG, doped with cerium. So YAG doped with cerium is a phosphor which is actually able to absorb blue light and emit yellow light. So it's what we call a fluorescent material. And although we don't cover fluorescence in detail until fourth year in 4MD3, when I teach 4MD3, we cover fluorescence in detail. The basic idea is that it absorbs photons of one wavelength and emits photons of another wavelength. This particular compound can very efficiently absorb and emit photons. So it has about a 95% quantum efficiency, which means 95% of the incoming blue photons emerge as yellow photons. By the way, that phosphor was one of the phosphor materials which was already manufactured by Nichia. So it took Nichia almost no time at all to add this phosphor that they had to the new blue LEDs that Nakamura had achieved. And they were able to produce white LEDs incredibly quickly. And of interest, special interest on this topic is the fact that Nichia filed patents about the use of this phosphor to create a white LED. And those patents turned out to be the most robust. So Nichia was able to block several other manufacturers from freely using the phosphor material YAG-cerium for making white LEDs. And those patents in particular forced agreements where other companies would pay royalties to Nichia. And that was a very successful strategy. By the way, today, YAG-cerium is still the most important conversion phosphor to convert blue light into yellow light. Although more phosphors of different formulations are being employed to increase the spectral range or the color quality of LEDs, because the color qualities should really produce light that's not just yellow and blue, it should also include green and red wavelengths. The human eye detects yellow light if it's combined with blue light as white. So some of the blue wavelengths that came from the gallium nitride material itself would actually emerge as a blue light, and the yellow light from the YAG-cerium would emerge together with that blue light, and the result would be white light.